Okay. What do we have here? A lot of words. We have thermodynamics. We have heat transfer. We have MATLAB. We have fluid mechanics. Dirichlet. What is Dirichlet? We have temperature, viscosity, obstacles, one dimensional. Okay, what dimensional? Okay, we have a lot of things here different. How can we actually associate all of this? Mhm. So basically, it's like a tool that will help us understanding a lot of physical phenomena. And the thing in between is just partial differential equations. Welcome to the course Computational Thermofluid Dynamics. And yeah, this is my face. This is how I look like. So, welcome again to the class. I want to present myself. So, I'm Camilo Silva. I have been doing this course for already like 6 years, more or less. And it's been a success. I'm super happy of the answer that I have obtained from the students. Mhm. Basically, because this is something, or this kind of course is something that I wanted to have when I was a student, and it didn't exist. Mhm. Why? Because actually, it's a way of joining two ways of learning computational fluid dynamics. So on the one hand, normally when we go to a course of computational thermofluid dynamics, you are given a commercial solver, and then you have to learn the theory somewhere in a manuscript or in a handbook, and then you have the actual interface where you actually make clicks, and you somehow learn CFD. Mhm. But this is not actually learning CFD. This is actually learning how to do clicking, and maybe the theory is super disentangled from the actual equations you are, or from the knowledge you have in the CFD subject. So, on the other hand, you may have also CFD classes when you learn how to discretize the one-dimensional heat equation, which is also fine. It's fine, but there is a big step between one-dimensional heat equation and two-dimensional, three-dimensional Navier-Stokes. Mhm. And when I was designing this course, I decided that the best way of learning is actually learning by doing. So when you actually have the capability of having the software developed by yourself, so you code your equations, and then you just realize the complexity and what is behind any kind of CFD solver or a typical CFD solver. And to be sincere, coding one-dimensional systems, this is completely fine as a first step. But in order to get the idea of how spatial coordinates in a physical matrix is mapped into a computational matrix, which each row is an equation for a node, for example. This kind of transformation cannot be captured if we do not go more than one dimension. We have to go at least two dimensions to really understand these different things of a matrix that is a computational matrix or a matrix that is a physical matrix. And this is something you can acquire in this class. So normally at this moment when I'm talking about this, I will give you the scripts and you will introduce yourselves. Okay? Okay, this time it's gonna be like that almost, but a little bit in a different arrangement. So today I will just introduce the theoretical part, and when we meet each other next time, so actually the first time, so you will introduce yourselves, and I'll give you the manuscript, okay, you can download it from the internet. You can actually have it also in ResearchGate if you're interested. Mhm. Okay, so I will start by showing you some studies done before by previous students to give you some kind of motivation of what you will be capable of doing at the end of the course. Okay, and then we go to the blackboard again, virtual blackboard, but I think the essence of the class will be maintained. Okay, so goodbye. So you will say goodbye to my face right now because I will not show up anymore in a video. Well, maybe from time to time. Okay, so this is the first slide. Computational Thermo-Fluid Dynamics, session 1. So my name, Camilo Silva, and Professor Wolfgang Polifke. He's the one who is the responsible for the department and also all these courses we offer. And Kilian Ferna, a former PhD student who contribute a lot for the building of this course. So, well, let's start. So, we all like physics. We love physics. And we want to solve physics. So, for example, maybe we like superconductivity, or we wonder how fluid dynamics can be described in this kind of flow, or we like electromagnetics, or we like how the flow over an oil flow looks like. But we could be even more exciting and seeing how does the shock wave looks like if I model it in a CFD solver, or how can I describe the temperature evolution that is like a very turbulent evolution in a continent, or how can I express just waves from a source that can be from different nature, acoustics, hydrodynamic, or how can I just express how the flame is swirled by the surrounding air. So all these has the same answer. Everything can be expressed in the framework of partial differential equations. Right, wait a moment. It's not cool to use PDE solvers as a black box. Even better, we can build our own PDE solvers and they become a transparent box. What can be better than that? In a big picture, this is going to be the content of the class. So we will start understanding the finite difference method. As I told you, we will discuss the one-dimensional case, but also we go directly to two dimensions. And also, we will consider heat conductivities that are actually not uniform, which makes the problem even more interesting. Then we have actually, this is one of my believed topics, the one I like the most is finite volumes. So the idea here is that we will solve the same heat equation, but now we will introduce a non-Cartesian grid. And this non-Cartesian grid makes possible the potential consideration of more complex geometries, as you will see, for example, in your projects. In the last class, we will consider also the Green's functions as a way of understanding the solution of a linear partial differential equation as the heat equation. And we can go more than that. We can actually become like in this matrix film when you look at just beams of zeros and ones and you understand what you're talking about. Okay, maybe it's not as exaggerated as I just said, but at least you will be able to observe a matrix like this one and understand what kind of system maybe these metrics representing. For example, if you look at one row, you will see, here I have 1, 2, 3, 4, 5, 6, maybe 7 nodes that are blue, which are actually non-zero nodes, which means that these nodes are related. And you may assume that this can be actually a discretization of a second partial, a second order derivative. And this is actually the case if we consider the Laplacian in our heat equation. We will see how to solve this linear system is crucial to actually obtain the answer that we desire as the output of the partial differential equation, which is in our case the temperature. A very interesting part is when we actually solve the unsteady problems, when you realize that these are two different things. On the one hand, you discretize operators in space, and on the other hand, you have the time discretization. Sometimes I have seen classes when these two things are mixed up, and basically it can be super confusing for someone starting to understand partial differential equations. That's why I maintain these things separated. So from the one hand, we first get experts in solving the spatial operators, and only then we will be able to tackle the time discretization approaches. And the interesting part here is when we talk about convergence. So this, maybe you have heard about this CFL condition and so on. We will also talk about this in here and realize that if we have a right evaluated time step for discretize the time in our equation, everything is going to become as we wanted. So we will have, for example, in here in this example, a large temperature in this wall, and we have some surrounding atmosphere at a given temperature. And then when we actually make things move, we will realize that there is a diffusion of temperature, so heat flux going outwards this body, which is actually a fin for cooling, if you want to think about it. But what happens if you actually do not choose the time step as you wanted or as you should have? Then the solution is going fine, you are happy, but suddenly everything blows up, and then game over. If you see in here, it's the same thing, everything looks fine, but suddenly in this region you will have problems and everything crashes. And it's a very good idea to know from the beginning at least good estimates on which is the delta T you want to use to avoid this kind of explosions. On all this is going to be done by whom? And this is all done by you. So you will actually love your code as your babies. You will see. Because during the whole course, we will start implementing solvers from the very beginning and putting layer over layer over layer until having really interesting stuff at the end of the class, at the end of the course, that you can use directly in your projects. Okay, let me tell you about some projects the students did like some semesters ago. This is one of the first projects I really liked that I did it together with some students. I started by bringing some attention of this test rig, which is why is moving? Okay, let's forget about that. Then we have here the methane and some air coming inside, and then this air is gonna be mixed with methane. There will be have some solar in here, and then we have here the flame. Okay, and the thing is that the flame is moving, and this flame surface area is changing, producing some acoustic waves. And these acoustic waves can actually go outwards from the domain, and then they come back reflected by some walls or some surfaces in the surroundings, and then you will have actually like a resonance inside the combustion chamber, and that can cause failure in engines, for example gas turbines in aircrafts, or the typical example of rockets some decades ago. And the students Thomas Runte and Gilles Raymond, they actually solved this with finite volumes in MATLAB, where you can actually visualize how the acoustic fluctuates. Let me just put it like this. It fluctuates. You have the crest, maximum, minimum. You have the pressure notes, and this is beautiful because in my experience it was the first time I coded something, or let's say I led a project so that the students coded something from scratch in finite volumes of this complexity. In special, Thomas, he did afterwards a semester bite with me, and it was so good that it became a journal one year after. So this is what I wanted also to stress. If you are interested in CFD and you do nice things, we can actually afterwards do some master studies, semester arbeit, bachelor arbeit, and then we may have even journal published. So this is amazing. I didn't expect that, and actually it has happened several times already. Okay, this is again an acoustic project. In here you can visualize this nozzle coming from a rocket. When you look at the cross section of this nozzle, you realize you have just a circular domain. And this is after discretizing this with also finite volumes. The students Felipe Pires and Alvaro Salas, they managed to solve the eigenvalue problem to obtain the different modes. So the pressure structure or pressure distribution that happens when a source is fluctuating at a given special frequency. That was a nice project as well. This project here was also beautiful. This was one of the projects that has maintained a very high quality. I mean, it brought the standards of the class beyond my expectations, and it was a nice work. They solved the stream function vorticity equations in an area expansion like this. So you can see here the velocity profiles. So first you have a parabolic profile, then you have here recirculation zones, and then you have the evolution of your profile until obtaining this. I remember that when I was reading this report of the final project, I was very happy. They also maintain these scientific standards in comparing with analytical solutions if they were available, or even some experimental measurements available in the literature. And this is something that I will like to push you to do, is having a topic that you really like, that you want to understand everything about it. So you start from the beginning, writing the solver that will solve the questions related to the problem, and then you just write the report as beautiful as you can to fit, I mean, to do great job. And then maybe if we can work together afterwards for a master thesis and so on, as I already told you. This is related to an airfoil. these kind of projects, we have several of them. I will show you one. This one maybe one of the best. It was the students Francesco de Crescenzo and Guillermo Duarte. So the nice thing of this project is that they were able to use finite volumes to predict the lift and drag of a given airfoil, and the challenging part here was to have the angles of attack that is non-zero. Normally you can do this by solving the potential flow. You will see it if you are interested, but normally you have to impose an additional condition at the trailing edge, so the Kuta condition, and this is not super straightforward, but if you like it, you do it, you solve it, and you have very nice results as they did. So this is something you can have back in your minds if you want to do something like that for the projects. This was an interesting one actually. I remember it was also the first generation. They wanted to do a tsunami from the beginning, and I was, what, a tsunami? This is a big thing. But anyway, we say, okay, maybe not a tsunami, but let's solve the shallow water equations to see if you have a strong perturbation in a given surface of the sea, let's say, how this perturbation propagates. And this is something that I can show you in here. So they did it. I have to accept that the code was not super, I mean, we're all learning, so it wasn't super efficient. So they have to wait hours and hours and hours until the solution was actually available. But I have to say that the job was beautiful, and there has been other two projects after this one where the propagation of waves based on these shallow water equations are solved. So this was done by Nicolás Mertz and Diego Villaplana. This is also a nice one. Is also about acoustic waves, as the first two I show you, and they are actually propagating from some, let's call it, injectors of acoustic waves. So you will see how they propagate. There are some interaction of the acoustic waves in here, and they form some interesting patterns. I would like to continue with this project because there is interest in our department to work on this kind of domains. When in addition of this, you have some sources of heat and also sources of acoustic waves in this region. So this is something also I encourage you to talk to me as soon as you want what you want to do. This one is very nice. This was about sources, but the sources that produce acoustic waves, they can be somehow non-symmetric. And the nice thing is this is solved by the linearized Euler equations, when you actually introduce the role of convection. So you have this so-called Doppler effect. Okay, here there was some numerical instabilities because this problem was not easy at all, but I like at least the first part of the evolution. In this one we have also something similar with a dipole. You will see how the acoustic waves are propagated, and you can also inject some mean flow in the Euler equations. All this was done by these two students who work hard, really, but I really was really happy of the results they got. Okay, so right now we will start with the actual theoretical part. And the first thing I want to show you is when you look at this kind of flow that is pretty complex. I mean, you will at the beginning, you may be scared even of how to confront this kind of problem. But classical way we have maybe learned from several courses already is the consideration of a control volume around the surface, and this is what we'll see in the next video. Okay, so let's meet in the next video. Bye.